Hello, in this video, I will be talking about test of independence and test of homogeneity. So let's start with the test of independence, which is actually called the chi-square test of independence. The chi-square independence test can be used to test independence of the two qualitative variables. So you will realize that this type of tests that we are doing in this chapter using the chi-square distributions are a lot different than the other type of test. We are talking about independence of two qualitative variables. And the alternative hypothesis will look like this. There is no relationship between variables, or the variables are independent. And the alternative hypothesis, there is a relationship between the two variables, or the variables are not independent. And there's the symbol to show that what is on the top here will actually be written on the bottom. That's why this is called actually the test of independence. If the null hypothesis is rejected, we conclude that there is some relationship between the variables, or we will say the variables are not independent, the variables are dependent. The assumption for the chi-square independence and homogeneity tests. One, the data are obtained from a random sample. We've seen this before. The expected value in each cell must be 5 or more. Note that these are the same assumptions as for the goodness of fit test. In order to test the null hypothesis, one must compute the expected frequencies, assuming the null hypothesis is true. So again, we are dealing with expected values, expected frequencies. However, how will we see the difference between what we've done in the previous video, the goodness of fit test, and the independence or homogeneity test? In this case, when we are doing independence or homogeneity test, we will see the data given in tables. And you do recall contingency tables. We used these tables in the previous chapters, and now we will be dealing with contingency tables again. Suppose the chi-square independence test is conducted using data from a contingency table with R rows and C columns. Again, keep in mind, we will be seeing information recorded in tables. And then the degrees of freedom for the chi-square distribution will have this formula: number of rows -1 times number of columns -1. If you are wondering how the test value or the test statistic formula looks like for the independent test, here it is. Chi-square is summation of the observed minus expected values, quantity to the second power, over the expected value. You've seen this formula before in the goodness of fit test. So we will be dealing with observed values, and we should be able to find expected values. And then putting in this formula, we should be able to find chi-square. Degrees of freedom, though, in this case, will have this formula. And to compute the test statistic, we must find first the expected values. For each cell, we should use this formula to find the expected value. So if we were to do this by hand, we will have a lot of work to do. This is tedious work. However, we will be doing this using the calculator command for independence test. And the calculator command for independence test is as simple as chi-squared test. But in order to do the chi-squared test, which can be used for independence and for homogeneity type of test, the first thing we need to do, we need to put the table in a matrix. So we have to get to the matrix menu and enter the numbers from the table in one option, and usually we use A, edit, and then we will run the test. As long as we have our values in the first or A matrix, after we run the test, you will realize that the expected values actually will appear in B. We will press calculate to find the test statistic and the p-value, and we will conclude the test. We can do these problems using the critical region method. For that, we need the chi-square table to figure out the critical value for the chi-square right. Keep in mind, all of these tests are right-tailed tests. So let's see how does this work on an example. Here is the first example. The report on an experimental flu vaccine was as follows. In a trial involving 1,602 children, only 14 of the 1,070 who received the vaccine developed the flu. Of the 532 who received the placebo, 95 developed the flu. Based on this, does the vaccine appear to be effective? Use alpha equals 0.05. So let's write down the given information. And we don't really see a table here, but based on the fact that we have this given information, we can actually create a table. Many times the tables are given, but if they are not given, you have to do that work of identifying the variables and creating the table. So let's see, what is this all about? Well, this is about children that received the vaccine, developed the flu or not. Children that received a placebo developed the flu or not. So I would say that I can organize this information in a table that looks like this. First of all, vaccine or treatment and placebo. And that will be the variable on the rows. And now we have to answer the question, developed flu or not? So we can organize this information in the table. We have some that did, even though they got the vaccine. Some didn't. So let's see, how do we place the information? We know that we have 1602 and only 14 of those who received the vaccine developed the flu. We have 14 that developed the flu, and out of this, we are left with 1,056 that did not develop flu. The total number is 1,070. Now, 532 received placebo. 95 developed the flu. So 95. And then if I subtract 95 from 532, I am left with 437. Total, we have 532. So this 532 plus this 1070 will actually be 1,602, the total number in this trial. Alpha is 0.05. Question, does the vaccine appear to be effective? In other words, is there a relationship between the two variables? What are the two variables? Getting the vaccine or not, and developing flu or not. Or I can say flu and vaccine are dependent or independent. So let's write down the steps. Step 1, setting the hypothesis. Well, the hypothesis in this type of problems will be written in words. I will say the flu and vaccine are independent. And let's just use this because we are doing a test of independence. And using this word makes sense, but it's the same as answering this question right here or this question right there. And the alternative hypothesis is the flu and vaccine or vaccine status, these are the two variables, are dependent. Let's just use the word dependent or not independent. From this question, it seems that this is the claim and this is a right tail test. These chi-squares are all right tail tests. I will go ahead and write down step 2. We are using chi-square distribution and the degrees of freedom, number of rows -1, number of columns -1. So in this case, we have 2 rows and 2 columns. So I have 2 minus 1 times 2 minus 1. So degrees of freedom for this problem will actually be 1. On the calculator, I will simply do the chi-square test. Now, before doing the chi-square test, I need to take this table right here and enter this in a matrix. Enter table in matrix. So let's do so. In order to get to matrix, I will just do second and x raised to the negative power, because right here we have the matrix option and we will edit this matrix. So let's go to edit and I'll place these values in the first one. And I need a 2 by 2 matrix. These are the observed values. Okay. And now use arrows, hit enter and use arrows. And of course, put in the values. We have 14, hit enter. And then we have 1,056, hit enter. You have 95 and 437. Okay. This is all you need to do. Now, I want to tell you something else. In case the table is given to you, and sometimes that will happen, and you have partial total. So right here, you'll have the total, and the total will be right here, 1070. It's in the problem, right? And right here, it will be 532. And then you'll have another partial total here, and then a grand total right here. Do not enter these partial totals and the grand total in the matrix as you perform an independence test, okay? So whenever that happens, just make sure you focus on the variables and only the values observed should be entered, not the total, okay? Now that we have that in there, let's run the test. I will get to stats and test. And we know these chi-square tests are on the other screen, so I'll scroll up. And right here, option C is the chi-square test. This is a test that needs to be used, testing independence and homogeneity. And here we go. Do we have the observed values in A? That's all you need to make sure you do before running the test. Don't worry about the expected values. Okay, just scroll down and calculate. And as you calculate, you will see degrees of freedom 1 and the p-value. So chi-square, which is the test value, it's 153. This is a very large chi-square. If you think of the values, this is into hundreds. So it should make sense that the p-value is so small, and it is indeed. Look at this p-value, look at the exponent 10 to the negative 35. So this will be so small that practically and theoretically it's 0. Okay, now I want to show you something else. If you're asked to find the expected values, just run the test because the expected values actually will appear in your second matrix. So right now, if I go back to the matrix, you see a second matrix appeared, and this is actually the matrix containing the expected values. So if I scroll down and hit enter and then hit enter again, these are the expected values. 72.80 was the expected value for our first cell right here, and then 997.19 for the second one, and so on. So this is the matrix of the expected values. Whenever the question is find the expected value, you can use the formula that I've shown you at the beginning of the video, but the easiest way to get there is by running the chi-square test and then look back at the second matrix that will appear there. That matrix contains the expected values. And now we will get back to our test and conclude the test. Here is step number 4 is decision time. And decision is based on the p-value method. And of course, we had zeros. It will always be less than or equal to 0.05. So we will reject h sub 0. And we will say at 0.05 level, and actually at any level, even 0.01, 0.001, right? But in this case, they ask us for 0.05. There is enough evidence, actually it is overwhelming, right? To support the claim that flu and vaccine are dependent. Or just to go back to the question, I will say that the vaccine is effective. And this is the test of independence. On a similar fashion, we can use the chi-square test for tests for homogeneity. Homogeneity of proportions test is used when samples are selected from several different populations, and the researcher is interested in determining whether the proportion of elements that have common characteristics are the same for each population. So right here we have the formal way we can write down the hypothesis. The proportions are the same, and H sub A, denoted also H sub 1, at least one proportion is different from the other. When the null hypothesis is rejected, we can conclude that the proportions are not equal. Okay, we've seen this type of stating the hypothesis in the previous video, which was related 2 goodness of fit test, those proportions referred to frequency distributions, to fitting a specific distribution. Okay, you will see using the next example how this homogeneity of proportion test is different. A researcher selected a sample of 50 seniors from 3 area high schools and asked each of them whether or not they drive to school. The data are as follows. So we have school 1, 2, and 3. That's one variable. And their answers, yes or no, that's another variable. At the 0.05 level of significance, there's the claim that the proportion of students who drive to school is the same at all 3 schools. First of all, looking at this problem, we see the information which is displayed in a table. So that's one way of trying to think, okay, this is a table in which this may be an indication. That's the first thing you should see. I'm dealing with a contingency table. I have 2 variables and I'm looking at the relationship between the variables. And this is a very specific relationship between the variables, and that's why this is called a test for homogeneity. We want to see if the proportion of students who drive to school is the same, okay? But look at this. This is a contingency table. So you should know that you should be thinking of a chi-square test. Let's go ahead and write down the given information, even though it's already there. We have 50 seniors, so the sample size is 50. We have 2 variables. Make sure you know how to identify the variables. One is the school, and the other one is the answer they gave to that question, yes or no. Okay, alpha, it's 0.05, and the question is the proportion of students who drive to school the same? So proportion of students that drive to the first school is the same as the proportion of students who drive to the second school and the third school. So we can see we have proportions and we have to check if they are the same. And it's not just for 2 proportions. We've done samples for 2 proportions and we use the 2-prop z-test. In this case, we are looking for more than 2. So let's go ahead and write down the information and go ahead and do the test. H sub 0 and H sub A. Well, it's already there. Proportion of students who drive to school is the same for all 3 schools. And the other one is, at least one is different. We can see that the claim is the first one. So we write down the claim. We know this is right tail test. So we'll go ahead and write down that we are using the chi-square distribution because this is a test for homogeneity. The degrees of freedom are row -1 times column -1. We have 2 rows and 3 columns, so it will be 2. And we will do the chi-square test. And again, we will do it using the p-value method. If we have to do it using the critical value method, we have to use the table, but it's a lot faster and easier to do it using the chi-square test. So here we go. I will show the work on the calculator. So the first thing we need to do is enter this table in a matrix. Second, x to the -1 will get us to the matrix screen. We will use arrows to get to edit and hit enter. And now we want to edit this matrix. I have the values from the previous problems in here. I have a 2 by 3 matrix. So it will be 2. And now I have to change this to 3 and hit enter. And now I'll just simply have to enter the values. Keep in mind, we are entering only these values without the total. These are the values that needs to be entered in your matrix. So the first one is 18, and then 22, and then 16. Then we have 32, 28, and 34. After you are done, you go back to stats, pick the test from test. This will be the chi-square test, and run the test. As long as you have the observed values in A, everything is fine. The test will calculate the expected values in B as soon as you hit calculate. Here we go. We have the chi-square and this is the test value or the standardized test value, is 1.59. I'll actually round it to two decimal places, is 1.60. And the p-value is 0.4503. That's a very large p-value, okay? 0.4503. Now, if you're curious and you want to see the expected values, go back to your matrix, second x to the negative 1. You see this second matrix appeared. This time is a 2 by 3, and hit enter and hit enter again, and you will see these values. And you can use arrows to get to all of these, but these are the expected values, okay? Or you can simply get to second x to the negative 1 and get to edit this time this one, and you will see actually all of the values. These are the expected values. Now we will continue with the test, and we are ready to conclude this one. Here is the decision. The decision is based on p-value method. So we have a large p-value. I haven't seen this in a long time. And this should be compared to 0.0500. This is large. So we will fail to reject age sum 0, which means at alpha equals 0.05 level of significance, there blank enough evidence to blank the claim, and simply copy down what the claim was. The proportion of students who drive to school is the same at all 3 schools. So you want to stop the video and fill in. We fail to reject the null hypothesis. We do not reject it, okay? Which means there is not, because when you fail, you always start with is not enough evidence to reject. We're not rejecting the claim. This concludes the video. Thank you for watching.